our final rate problem is an opposing rate problem. I like to think of these as moving walkway questions. So you are probably familiar with the moving walkways at the airport. They are like horizontal escalators that can help you walk down long hallways. And so if you have a person and he is moving with the moving walkway, so perhaps the person he is walking, so he's walking at a rate of, we'll say 3 meters per second, but then the walkway under him is also moving at a rate of 2 meters per second. And so in this case, after 1 second, the person has walked 3 meters, but the walkway has also pushed him an additional 2 meters. And so it is really like he is moving at a rate of 5 meters per second with the walkway. Now, you are probably also familiar with a scenario where at the airport, there are a bunch of punk kids who are not being watched by their parents. And so the walkway is still moving from left to right at 2 meters per second. And the kids think it would be fun to run across the walkway in the opposite direction. And so now they are going from right to left at a rate of 3 meters per second, getting in the way of everybody trying to go to their terminal. So now in this case, after 1 second, the kid has moved 3 meters to the left, but the walkway has pushed him back 2 meters. And so it is really like he is moving forward at a rate of 1 meter per second against the walkway. And so this here is really the opposing rate situation. But if they were to give you a moving walkway type scenario, they can present them both, it can be an additive or a opposing rate situation. And so let's look at a GMAT problem that does that. Two islands, Island A and Island B, are 900 meters apart. Nemo swims in a straight line from Island A to Island B and back. At a constant rate, it takes him 7.5 minutes to travel from Island A to Island B, assisted by a downstream current. It then takes him 12.5 minutes to travel from Island B to Island A against the current, also at a constant rate. Which of the following most closely approximates? So that is always a keyword. How long it would take Nemo to travel from Island A to Island B in still waters. So still waters means with no current. That would be like walking without the assistance of the moving walkway. So here we have 2 parts to our trip. So when he's going from Island A to B, Nemo is going with the current. And so if we say this is Nemo, this here is the current, and then he returns from Island B, the current is still going from left to right, but now Nemo is going in the opposite direction. So for the second part of the trip, he is going against the current. And then what else do we know? What can we fill in? So our distance for each of the 2 legs is 900 meters. And the total distance of our trip is 1800 meters. And then we know the times for each leg of the trip. And so I prefer writing them as fractions. So 7.5 is 15/2. And so it looks like our unit here is meters per minute, which you want to take note of. Sometimes you might have to convert between meters per minute or meters per second and kilometers per hour. Then for the second part of the trip, it took him 12.5 minutes, which is 25/2. And that makes sense because when he is going against the current, it should take him longer, assuming that he's moving at the same individual rate, which they say he is. That is what they mean by a constant rate. And so we want to know how long would it take Nemo without any sort of assistance from the current to go the 900 meters. And so it looks like we've pretty much have this entire thing filled out. We can figure out our rates from the distance and the time that we filled in. So the question is, but what rate is this, and what rate are we looking for? So this here is Nemo with the current, right? So this is Nemo's individual rate plus the current's rate. Now here, this is Nemo, this is still the current. Now this rate here is when he's opposing the current. So this rate would be Nemo's rate minus the current's rate. And so if we need Nemo's time by himself, we need Nemo's rate by itself. And so you have to separate out our rates here into their individual components so we can isolate just n. And so what I want to do is I want to solve for Nemo's individual rate, then use his individual rate to find his individual time. And so now if I want to make equations out of what I have, I know this times this is equal to this. So n plus c times the rate times time, 15/2, is equal to 900 meters. And then n minus c times 25/2 is also equal to 900. So if I want to get my n and c by themselves, so here I will multiply each side by 2/15. And so we get n plus c is equal to what? So 900 times 2/15. How should I do that? So I can break up 15 into 3 times 5. So then I get a 300 here. 300/5 is 60. So this is just 120. And so this is Nemo with the current. This is the rate of Nemo with the current. So our unit here should be meters per minute. So n plus c is equal to 120 meters per minute. Then here, n minus c should be equal to, I want to multiply each side by 2/25 to cancel out this fraction. So 900 times 2/25. And what does that give me? So 25 goes into 100 4 times. Therefore, it should go into 939 times 4, or 36 times. So this should be 72 meters per minute. And again, that makes sense. When he's going with the current, he's going significantly faster than against the current. He is almost half as fast against the current. So now what did we say our goal was? We want to solve for n. And whenever I'm solving systems of equations, I like writing them out like this. I like writing them vertically with my variables lined up, because people always like to, when they have systems of equations, most people are always trying to substitute. And I very rarely am doing substitution. I'm always trying to combine my two equations to solve for what I am looking for. I think it is easier and less prone to math mistakes. And in this case, I am trying to solve for n, meaning I want my c to cancel out. And my equations are lined up very nicely, so that if I just add them, the c should go away. So if I add the two equations, 2n is equal to 192 meters per minute. So Nemo's rate is just 192/2 meters per minute. What is that? 96. So Nemo can swim at a rate of 96 meters per minute. You can tell me if that is makes him a fast or a slow swimmer. So I am not done yet because I have to find the time, right? The time for Nemo to go the 900 meters. And so now it is just a final rate times time equals distance. But here we are used to the distance is 900 meters. It is individual rate, 96 meters per minute. And then it said approximately, right? So that is a hint that I might not get a round number here. So time is 900 over 96. If I want to simplify that now, the digits of 96, they sum to 15, which is a multiple of 3. So 96 should be divisible by 3. So if I divide each of these guys by 3, 900 divided by 3 is 300. 96 over 3 is 32, I think. And then I can simplify this a bit more. So divide each the 150 over 16. Then divide by 2 again, 75 over 8. So 75 over 8 meters per minute. So if I put that as and I'm sorry, this is just the time. So it's 75 over 8 minutes. Again, another reason to keep track of your units as you go. So if it takes them 75 over 8 minutes, I probably just need to convert that to a decimal or an approximate decimal. So 75 over 8 minutes, 75 over 8. So 8 goes into 75 9 times with 3 left over. So 9 and 3/8 minutes. And so given that answer choice E is the only answer choice over 9 minutes, 3/8 of a minute should be approximately 20 seconds. That sounds right. But E has to be the answer choice.